Hello, my name is Seokbin Lee. I'm honored to be able to participate in this session, and I'll be talking about my topic of research, Grassmannian as continuous abstract data type with computable semantics. I was an undergraduate when I performed this research, and I was supervised by my professor, Martin Ziegler, and was advised by two senior members, Dong-hyun Lim and Se-won Park. So let's begin. So first we need to talk about what a Grassmannian is, and to put it simply, we can think of a Grassmannian as a subspace of a given vector space. So we can think, so an example would be a three-dimensional Euclidean space, where the basis vectors are given by the standard basis vectors, right? And in a more formal sense, we can denote the Grassmannian as like this, as a subspace of a vector space, which we will denote like this to indicate that its dimension k and a subspace of a vector v, vector space v. So this is the example that I talked about. In the Euclidean space R3, this will denote the set of all lines in R3, and this will denote the set of all hyperplanes in Rn, which all pass through the origin. And we want to represent these Grassmannians as matrices. This is the basis for our research. And one intuitive way of doing this is, as is typical in linear algebra, denote the basis of the Grassmannian space as column vectors in a D by M matrix, where M is the subspace dimension and D is the ambient dimension of the vector space. Right, and computation of such operations, we will define these, and how we will do so is by using these matrices, which will define, right, so the operations and the computation of these operations will be defined with respect to such a basis representation. So let's talk about the operations on Grassmannian elements that we will look into as part of this topic. So let's say A and B are Grassmannians, so they're subspaces of a d-dimensional vector space. We want to take four operations. We are interested in the complement of A with respect to the ambient space, the join and meet of two spaces A and B, and the projection of the space B onto a space A. And this is the formal definition of it. So the orthogonal complement is just a set of vectors which are perpendicular to every vector in A. So as an intuitive example in linear algebra, okay, I skipped over the slide, but so if we have the set of one-dimensional lines in R3, the complement of that space would be the set of all planes orthogonal to that line, right? And given Grassmannian elements A and B, this set is the join, or the Minkowski sum, and this is the intersection set, where this intersection is the set theoretical intersection of two spaces A and B. Right, and finally we define the projection as follows, and this is a diagram to sort of indicate how we will be defining this. So suppose we have two elements A and B. This plane represents the space A, and this vector represents an element of this Grassmannian B, and this set will be the set of all vectors which have been projected onto this space A. So this vector is the projection of this vector onto this plane. So this set will be a subspace of this ambient space A, and it will consist of all the projected vectors of B onto this space A. Okay, so how are we going to implement these operations with these Grassmannians? Now, earlier we said we were using matrices, and we will be utilizing Gaussian elimination for the computation of these operations. But this comes with a hitch, namely that we can't test for equality in exact real computation, because it will be equivalent to the halting problem. So, in more formal terms, this testing inequality is semi-decidable. Right? It can't. Right. So explicitly testing such inequalities will not halt, and is therefore considered to be impossible in our paradigm. Right. So more specifically, we see that comparing an unknown variable to this constant 0 will be undecidable. Since if we could do that, we could also solve the halting problem, which we cannot. Right, so a workaround for this, as specified in the exact real computation paradigm, is to have a select operator. So this is the computable variant of a select operation. What it does is it takes two values b and c, which have one of three values, 0 or 1. So 0 implying false, 1 implying true, and this bottom, which indicates that these values are not computable. And this operation behaves as follows. If b is defined, so if b is not bottom, it'll return 1. If c is not bottom, it'll return 1. If b is not bottom, it'll return 0. If c is not bottom, it'll return 1. And if either is defined, well, we can return either 1. And if neither is defined, it'll also return bottom, which is to say, it'll not halt in computing this. Now, if we can think of this as intuitively as a machine that keeps calculating more and more precise inputs b and c until one of them reaches a halting state, we can see that this is computable. I won't go into details here because it's not the main focus of our topic, but the important thing to note is that this operation is indeed computable. And we can use this as a workaround for the earlier problem of not being able to test equality with 0. Right, and the main results of my talk will be in giving specifications for Gaussian elimination that does not explicitly check for 0, but instead uses a select operator, which we know to be computable. So this is one example of what we'll be doing. So, for example, if we have a matrix and we want to locate a non-zero entry, we can't explicitly compare for 0 because, again, that's impossible. But what we can do is we can switch rows as we like, and we can row reduce it to 0, and we can continue this process until we get a Gaussian form of this matrix. Right, and more details on this later. Right, but one thing we need to specify is that the dimension of the output space is given as part of the input for the operation. So, for example, if we're trying to compute the meet of two Grassmannians, we want to also specify what the dimension of the output space will be. Right, this is part of the specification that we will demand in order to give an algorithm for this. Right. So let's get right into the operations. So this is the operation for the pseudocode. The pseudocode for computing the complement of a subspace A. So this operation starts by taking a subspace A and the demanding output dimension of what this Gaussian operation will be. So the most important thing to take out from this is that we want to, if we have elements A, if we have a matrix A, and we have this bunch of entries that we want to select, and we want to select one of these which is not 0, well, this satisfies the condition that at least one of these is not 0. And if we specify that one of these is indeed true, then we can take the index for which this select operation is satisfied. Now, this is the main crux of how this Gaussian elimination will work. And earlier we just described it as selecting from 2 values, but we can clearly see that this can be extended to an arbitrary number of entries. So this is what we do. We take these for ai, all the way to ai, n, and check to see which one is not 0. And once we found any one of them, we let j be its value, it be the index. And the rest is a fairly typical Gaussian elimination process. And if we iterate this for k rows, then we can get the matrix which is row reduced. And why this is important is because we can use this Gaussian operation. We can easily extract the complement of this Grassmannian A. So this is standard linear algebra. If we take the A, whose column vectors represent the basis for this Grassmannian, we can create this augmented matrix, perform the Gaussian operation on it, and return this submatrix of this matrix, which will return the complement corresponding to the Gaussian matrix corresponding to the complement Grassmannian of this Grassmannian A. Right. This is a bit of a mathematical justification for it, and this process is actually fairly standard linear algebra material, so I will not be explaining that in too much detail. Right, and moving on to the rest of the operations. So this will be applying Zassenhaus's algorithm, which works as follows. So if we have two spaces A and B, we make this big matrix, consists of 4 block matrices. We reduce it to this, where the top right is a 0 matrix. And if we do that, then C will be the join of the 2 matrices, and D will be the meet of the 2 matrices. Right, and this requires a bit of a different Gaussian elimination operation, but the idea is the same. So if we take these 2D times n plus n entries, and we demand that at least one of these is not 0 because A represents a basis for a space, then we can take the indices for one of the entries for which this is not 0. And we can keep doing this k times until we get a reduced form of a matrix. And this is the main idea behind this Zassenhaus's algorithm and row reduction. Right. So if we take 2 spaces A and B and get the output dimension L, we perform this Gaussian elimination. This submatrix will be the join of represent the join of the 2 spaces A and B, and D will represent the meet. So, right, that we basically get that for free. All right, and lastly, we want to compute a projection of a space B onto a space A. Okay, so this is actually fairly simple because in standard linear algebra, we get that this matrix will be the projection matrix onto a space A. And one thing to note is that this ATA matrix is regular. This is because A has column vectors which represent the basis. So computing this matrix, we get a square matrix which is invertible or regular in these terms, and we can easily compute the inverse of a matrix with various methods, including row reduction. So we can be given that this is computable, and we can always compute this matrix P, and then it's just a process of taking multiplying the matrices P by B, and then returning the Gauss eliminated form and returning the first D by L submatrix of this matrix. Right. So we actually implemented this in IRAM. The source code can be viewed in this GitHub repository, and that'll conclude my talk.